now we're going to look at autoencoders, which are a way of using neural networks for unsupervised learning. So we don't need labeled examples. We're going to see what are autoencoders and how we can force the autoencoder to learn something useful about the data. So being undercomplete, using regularization, sparsity, and so forth. And we're going to see examples of application to dimensionality reduction. You're going to do this on the tutorial part, but I'm going to explain this on the second hour, the example. So an autoencoder is a neural network that has as output, the objective is to have the network output the same as the input. So if we present it with an image in the input, we want the same image coming out of the network again. So this is why it's called autoencoder, because it's trying to replicate the same input. And the idea is that in the hidden layers, the autoencoder will create a different representation of the data that we're feeding. So here we have some image space, which we can consider to be the space of all possible combinations of values in images. And somewhere here, there is a region where we have cat images. And we want to map from this space to the same space here. We want to get the same thing out of the network. But somewhere in the middle, we have a mapping to a different space where the same images are represented, occupy a volume of that space, but are represented in a different way. So we can divide the autoencoder into two parts conceptually. If these two neurons here will have the encoding that we're looking for, this first part is the encoder, which maps from the space where the input data are into this encoded region, into this different space. And then we have the decoder part, which maps from this space in the hidden layer to the original space again. So this one here, in analogy with the latent variables in models where you have hidden variables that we don't know the values of, we have here, we call the latent space. So it's something that is buried inside the network. In this case, they are not quite hidden, because then we're going to use them to represent the data, but this will be a latent representation, or a representation in the latent space that we're going to create. So basically, the encoder will find a representation, the result of a function of the input. So this fx will be done by this first part of the network, and we have as the output here the values inside at the center of this autoencoder, and then the decoder does the inverse and brings us back to x. There is no need for labels, because we are trying to adjust the input and the output. We're trying to make it the same, so it doesn't matter if we have labels for the data or not. But the question is, what's the point of trying to do this? Because obviously we do not want a network to give us back the same thing that we put in. That would not be very useful. But the idea is that this representation inside, if we can force the autoencoder to do something useful, we can get a representation inside the autoencoder that has advantages like having a lower dimension than the original data that we're feeding into. It can capture some structure in the data, or represent different aspects of the data. And now these things can happen if we manage to force the autoencoder to learn what we find useful in some particular instance. So basically, we need to create some informational bottleneck here to make it hard for the autoencoder, so that the network doesn't simply copy the values from one side to the other, because that would be a trivial solution to this problem. So we must make it so that there is something that must be done to this information, so that in the middle the network will try to find something that we can then use. So let's see some examples of how we can force the autoencoders to do something useful. Basically, they are usually feed-forward networks. We can train with the same algorithm, backpropagation, minimizing the loss function. Since the target is the input, we don't need labels, so we can use any data that we have, even if it's not classified. But we need to force the autoencoder to do something, otherwise it will just copy the value. So let's see one example of what we can do is to use an undercomplete autoencoder. An undercomplete autoencoder is one in which the latent representation is at a lower dimension than the input. So this would be something like this, this scheme here, where we have an input with many more neurons than what we have in the center of the network. So we are forcing the network to encode this into a lower dimension and then to retrieve all the information from this lower dimensional representation. So basically we have this loss function, which is simply the difference between the output of the network and the input values. And if we create a linear autoencoder, one without nonlinear transformation, this is similar to principal component analysis. It's not exactly the same because principal component analysis has this additional constraint that the vectors must be orthogonal, but it's a similar thing because it's a linear transformation of the data. But since we can stack more layers in the network, we can create nonlinear transformations which are more powerful, arbitrarily more powerful. We can build the network with as many layers as we want, and so we can force the network to do a transformation that will try to represent the data better, adjust better to the regularities in the data, and use that smaller dimension in a more efficient way to capture that information. Now there is a trade-off here between two different aspects or two different extremes in the range, which is if the autoencoder is too stiff, too unable to adjust to the data, then it will compress the information, but in a way that cannot be used to retrieve the original data, and we will not have a good fit at the end. On the other hand, if we increase too much the power of the autoencoder, then we can make it so that the decoder part here contains a lot of information, enough information, for example, to generate all the images that we feed into it, and then this will simply index the image. Say image number 1, it outputs image number 1. Image number 2, it outputs image number 2. So at that extreme, all the information of the images would be contained in the network, and we would not have anything useful in the encoding itself other than different identifiers for the different images. So this is not really strictly a problem of overfitting, because the point here is not trying to train on one set and then generalizing outside that set, but it's a similar problem. We want the autoencoder to be able to compress the information and retrieve the original information, but without being everything stored in the autoencoder itself. So it must capture the data or the relevant information in that representation in the latent space. So this is one classical example. I showed this in the first lecture. This is Mitchell's autoencoder, which has the input vectors here are one hot encoding. They have 8 possible values, but only one of them is set at 1. The output, the network is trained so that the output is the same as the input for all the examples. And here we have 3 neurons in the latent space representation that will output values in different combinations representing all the 8 different possibilities. This was another example. This is the one you're going to do in the tutorial. We have this 4-dimensional data set, which are those banknotes, and if we do PCA, we get something like this with a lot of overlap, because this is only a linear transformation. But if we use an autoencoder, we can do a more a more complex transformation with nonlinear parts, and this adjusts better to the structure of the data, and we can see a better separation here. Note that this was not trained using the labels. It's just trying to input each value and output the same vector of 4 features. So the autoencoder is not looking at the labels. However, these 4 features are spread out in this 4-dimensional space in a way that can be projected in 2 dimensions, keeping this structure where fake banknotes and real banknotes are more easily separated. Another possibility is to use an overcomplete autoencoder, or one that is not undercomplete. This would be a bad idea if we use it just this way, because if the latent space has more dimensions than the input and the output, then all the network needs to do is to ignore part of these neurons and just copy the values over the network for the other neurons. So it would not learn anything useful. However, we have methods for regularization that we can use to force the network to learn in some particular ways, like keeping the weights as small as possible or as few neurons turned on as possible and things like that. So this would be the idea. We can use autoencoders that are not undercomplete, that do not shrink the dimensions, but we can use regularization. So regularized autoencoders, this is a family of possibilities where we use regularization to impose that bottleneck on the information flowing on the network. One example is the contractive autoencoder, where we have this original loss function. So this is the difference between the input, the x, and the output of the encoded input. So this would be the output of the autoencoder. Fx is the encoding part, g of fx is decoding back again. So this is just trying to make the output the same as the input. But then we add this term, which is a sum of the norm of the absolute values of the square of all the derivatives, the partial derivatives as of our neurons as a function of the input. So this means basically that we want our autoencoder to be less sensitive to small variations in the input values, because we want the derivative with respect to the inputs to approach 0. If we do this, we are trying to capture the shape of the data, so to speak, so where the data varies, and making so that our autoencoder will build internal representations that are similar for similar inputs. We retain the same kind of structure. So the autoencoder is more robust in this way. Similar examples will be close together in the latent space and will not result in a large change in the activation of neurons. And it also favors smaller weights, because typically, other things being equal, we obtain a smaller derivative with respect to the inputs if the weights of the neurons are small. So this is for this reason comes the name of contractive autoencoder. We can imagine that it's trying to shrink as much these values, these vectors here. So this will restrict the latent representation, this H in the hidden layer in the center of the autoencoder, to try to capture important aspects of the way the data is distributed. This is an example with an image and then a measurement of the most important singular values on the matrix of partial derivatives inside the network at different neurons. So we can compute the partial derivatives with respect to all the inputs. Remember that the inputs are multidimensional. We have many values coming in, and we can see what changes in the image make a larger variation in the output of the neuron. This is a comparison with PCA. So if we do PCA, we have something that seems random. So one pixel changing may make a large difference, another one not so much, but there doesn't seem to be any structure here. But when we do this with contractive autoencoders, we see that the sensitivity to the changes in input values will follow something that seems to be important for that kind of feature. So it's important, one neuron is giving some importance to this part, the other to this here, and so on, but it's all around the right shape to try to represent this kind of data. And the same here, this is an image of a horse. It's not, you cannot see it very well, but you see that unlike what happens with PCA, we see that those edges of contrasts in colors and shape and so on are more important for the neurons. So basically, with contrastive autoencoders, we don't need to reduce the dimensionality, but by using this regularization, we are forcing the network to focus on important features. And in the case of contractive autoencoders, the regularization is trying to minimize the sensitivity of the network to differences in input values. So we're trying to minimize the square of the partial derivatives with respect to the input. Another possible regularization is used in sparse autoencoders, where we try to minimize the probability of neurons in that latent representation being active. So basically, we have some probability for the neuron firing, and this is what we expect to be the average activation at that layer. So if the probability is, say, 0.1, we expect that at that layer only 10% of the neurons will be active for any example. We can try to force the network to learn to do that by adding to the usual loss term, where we are comparing the inputs to the outputs, also this Kullback-Leibler divergence using the Bernoulli distribution. So we're not going to go into detail on the formula, but the idea is that each neuron can be on or off. So with all the neurons we have a Bernoulli distribution, and we want to approach the distribution, the number of neurons that are on at each example, to what would be expected given some probability of the neurons activated. This is something that we define. So if we define that we want only 10 neurons active at a time, we are going to penalize any deviation from that expected value according to that distribution. So this forces the latent representation to conform to this that we're specifying. And so in this case, the network, even though there are many neurons available, for each example, it will try to use only that number we are telling it to use. This causes the neurons to try to specialize into specific features, and we have here an example of sparse autoencoders trained on images. These are, each of these image here is one single neuron, so it's either on or off, but the image that is represented there is the image that maximizes the activity of the neuron, subject just to this norm-bounded constraint. Because if you put something that is all white or all black, depending on the weights of the neurons, you can maximize the activity of the neuron trivially. But if we force that the total vector of the image has always the same size, we can find which parts of the image must be brighter or darker in order to maximize the output of the neuron subject to that constraint. So we have an idea here that, for example, this neuron is sensitive to bright edges at that part, this one to vertical lines here, this one to diagonals, and so on. So by imposing that sparsity constraint, because we are trying to train the network to fire only a few neurons at a time for each example, the neurons will become specialized to some features that sometimes appear in some examples but don't appear in others. Okay? So they spread out the work in a way that becomes more meaningful and potentially more useful. These are some different types of sparsity penalties. So without penalty, we see that the images that activate each neuron become a lot more messier because the neurons are not specializing so much. But if we use these penalties. So in this case, this is the MNIST data set. We can see a bit the shape of the numbers here. If we impose these penalties and force the network not to activate everything at the same time, but to activate only a few neurons for each example, they will specialize, and we can see, for example, using this Kullbaum-Leibler divergence, we can almost see the numbers here where the neurons are becoming specialized. Another way is to use denoising autoencoders. So this is another way of forcing the autoencoder to learn something useful, even though we are just feeding it the features and getting them back, is to feed the autoencoder with noisy data, with data that was where noise was added. For example, we choose in the case of an image, we can choose a random set of pixels and put them to white or black and just deactivate them. And we want the autoencoder to give us back the original image without the noise. So the autoencoder must figure out how to reconstruct the original image, even though it's being fed something that is partially corrupt. So this will be the representation there in the latent space. It will not suffice just copying the input to the output, because that will copy the corruption too, the noise. The autoencoder needs to figure out, so to speak, what is the structure of the data, so it can fill in the blanks, fill in the parts that are missing. And this kind of autoencoders can be used also to fill in parts that are missing from images. So say if you just cut away a watermark and then it can reconstitute the image, or if you took a photograph but there was a car going by, you can cut the car and it will fill in the image with something that is not real, but it's plausible because it looks like an image. So the algorithm here is simple. We just take one example, apply the noise, the corruption. Usually this can be done setting some of the inputs randomly at 0, so they are missing, so to speak. And then we train by minimizing the distance between what the decoder is outputting and the original data without the corruption. So we are forcing it to retrieve the original data. Denoising autoencoders are similar to the restricted Boltzmann machines. These are graphical models, probabilistic models, which have one like a layer of latent variables, hidden variables, and a layer of outputs, and they try to maximize the probabilities, the joint probabilities of the data and all those variables. So if we use denoising autoencoders that have just one hidden layer, and we use a sigmoid encoding and then linear decoding for the output, this would be equivalent mathematically to restricted Boltzmann machine. If we stack denoising autoencoders, then this would be equivalent probably to stacked restricted Boltzmann machines, but then it would be much harder to train in that case, because if you have many variables there in those graphical models, at some point it becomes impossible to determine all the distributions. But with autoencoders we can use backpropagation and we can just train the network. So they are equivalent in some extreme cases, but then they allow us to do more things. So in general, we can think of autoencoders as trying to learn probability distributions. These parallels with graphical models. Basically, we can think of the decoder as trying to learn the probability distribution of the X, which is the input to the autoencoder, but it's also the output of the decoder, given the hidden representation there, the latent space representation. We want to maximize the probability of the data given the model, so this is the maximizing likelihood, and this gives us those loss functions depending on the output. So, for example, if we're trying to minimize the distance between the image that is in the output and the image in the input, we can use a linear output and minimize the square error, which is the equivalent of considering that the error is in a Gaussian distribution. If we want, for example, to use autoencoders for one hot encoding, we have something that has a very large vector but only one and everything else zero, and we need the same in the output, then we can use the output as the softmax, for example. Then the loss function will be different, but the idea is the same. We'll try to maximize the probability of that data given the parameters inside the network, and so we adjust the parameters to maximize that probability. And we can think of the encoder as doing the same thing but in reverse. So basically the encoder is trying to maximize the probability of what it outputs, which is that hidden representation given the data and the parameters, and the decoder is doing it the other way around. It's taking that hidden representation as the input and trying to find maximize the probability of getting the values back. So one question that we can think here is if we can use this to generate data, because now we have this mapping in this way. So the encoder will map between the space of from the space of the images into that latent representation, and then the decoder will map from the hidden representation out again to the space of the image. So in theory, since we have this part that can map this way, this would be to create that special latent representation of the data, but we could then use one example from this latent space, and it would create the corresponding image. So if we could pick one example here in the volume of the latent space that corresponds, for example, to cat images, we would get a random cat image out here. That could be a new cat image that the encoder never saw, because this volume here would all correspond to cat images. We have a sample from there during training, but we could choose another one and it will also be a cat image. The problem is how we're going to choose a value inside this space. So basically we have two types of classifiers in general. When we have a discriminative model for classification, what we're trying to do, or classification or regression, but basically we're trying to predict the probability of some class or some value, the target value, given the features that we receive. And so we can classify by choosing the one that has the largest probability, because we can predict the probability of being in class 1, class 2, class 3, and so forth. A discriminative model tries to approximate this function. We saw this, for example, in logistic regression, where we assumed there was this function that gave us the probability of one point belonging to a class, given the features of that example. But we can do it a different way with generative models. Instead of trying to approximate a function that has the conditional probability of the target value given the features, we want to approximate a function that is the joint probability of the features and the target value. And this can then be used to find the conditional probability, because it's just, we need only the marginal probability of the features. Models like naive Bayes and so on can do this. And this is called a generative model, because if we have the joint probability distribution, we can sample from this distribution and generate something, both the features and the class, which we cannot do here, because here we only have a conditional probability. If someone gives us the features, we can estimate the probability of belonging to one class. But if someone tells us the class, we have no idea what is the probability distribution of the features for that class. So we cannot generate features for that class. But with a generative model, we can do that. Now, with autoencoders, we can have this intuitive feeling that it should be possible if we have an idea of what is the distribution for the features. But that could be a way of doing this. The problem is that if we don't have an idea of this distribution, if we pick one example inside the space that corresponds to representations of cats in this latent space here, then we'll get an image of the cat. But if we pick something that falls outside that space, then we get garbage, because this other value outside this space here will no longer correspond, will no longer map to pictures of cats. And since we don't know what is the distribution of this space, it's hard to tell if we're going to pick images of cats or not. We could do this if we knew what was the shape of the cloud, so to speak, of representations of cats. If we had an idea of what was that shape, we could pick samples inside that cloud and not risk going outside the cloud. So this is what we can do with generative adversarial networks. Instead of trying to find out what is the shape of that latent representation that the autoencoder learns, we decide the shape. So let's say the shape here is a set of Gaussian distributions for the latent representation, and this is what we decide corresponds to cats. We can pick a point from that because we know the distribution of probabilities. Of course, since the network is not trained, we don't have the correct weights here. If we pick an example here and pass them through the network, we get garbage because the network does not know how to map from that space to cats. But we already decided that that must be the space of the latent representation. So how can we train the network now to correctly map from that space to cats? We use another network that we train to distinguish cats from the fakes the first network is giving. So we produce a set of fakes, we feed them into this network along with cats, and this network will decide if an image is a fake image or if it's a cat image. So basically this network is learning to separate the space that corresponds to cat images from the space that is everything else, all the garbage. And now we can go back to the first one and use the responses of that net to help this one train. So this one will try to learn how to deceive the other one into thinking that it's receiving the image of a cat. This is why they are adversarial networks. This one will now try to, starting from points that we give here in this distribution that we decided, it will adjust the weights so that the response here, the image that is produced, give the highest score for being a cat in this network. And we train this first one until it starts to deceive the other well. But this may be because this one did not learn very well where the cat images stop and garbage starts. So it may be because this one is thinking that garbage images are cats. So now we go back to this one, and with a new batch of examples, we refine it so it can better distinguish between the fake and the real ones. And now we do this back and forth as many times as necessary. And as we jump back and forth, we improve one network and the other. So this takes longer than just training one network, but we can solve this problem because we cheated by fixing the distribution of points that correspond to the latent space representation of the cat. So we fixed that. We are not going to be uncertain about that because that's what we're telling the network. What we don't know are the weights the network must have in order to map from that volume of the latent space into actual pictures of cats. But this now we train with adversarial networks. This is an example of the progress in the last few years in generative adversarial networks. This is what was done in 2014, and this is an example in 2018. So this lady does not exist. This is not a real person. This is an image generated by a network that was trained adversarially with another network that tries to figure out if the images are fake or real. So at some point the network is good enough to produce these images. And there is the site, I think it's called Not a Person, where you can go and every time you refresh the page, you see a new face of someone who doesn't exist, and they are very realistic. So this is one solution for the problem of trying to find a distribution in the latent space where we can pick examples and then generate an example in the space of our data. But there is another way of doing this with autoencoders, and we can do this with variational autoencoders. So remember, the problem is that we don't know what the distribution in the latent space is that corresponds to that volume that maps into the data that we want. So with the variation of autoencoder, we are going to train the autoencoder and force the latent representation to conform to some distribution that we are choosing. So it's something similar to what we did here. We chose the distribution. We're going to do that with the autoencoder with both sides at the same time. So that's the way, if we can force that distribution and we know what the distribution is of the values in the latent representation that map to the images we want, then we can pick something from that distribution and generate data. So we can train the autoencoder to learn parameters for some distribution. And the idea here is similar to what we saw before. We use, again, the KL divergence as part of our loss function. So basically here we have the expected log of this probability of the output given the hidden representation. So basically this is the difference between the output and the images that we're using. So the usual loss function when we're training autoencoders. But now we have this Q distribution that we want the hidden values, these Z values are those in the hidden representation, and we want them to be in this distribution. So we measure the divergence with respect to that distribution that we choose. Typically, this is a set of independent sigmoidal distributions, and we measure the divergence between, with respect to that distribution we chose, of the actual activations inside the network. Now, the problem is that to do this, to measure the distribution of values inside the network is not very practical, because this is multidimensional. We have large vectors, and the way to try to estimate the probability distribution here would require a huge sampling of the points to get an estimate of how they're distributed. But if we can do this, then we are assuming this parameterized distribution. We know what it is. We want to force the network to have those values on the latent representation to be in that distribution. And so if we can do this, minimize this divergence while minimizing the reconstruction error, the difference between the output of the network and the input, then we will have a decoder that can create images, for example, or data like the ones we want, and we know what the distribution of the latent representation is. So this would be the solution to our problem. And so, for example, we can get a mixture of independent Gaussians here as the target distribution, and then just sample from the Gaussians, and we would be confident of getting good results then. The problem is how we measure this distribution. So the distribution probability of Z of the hidden representations is very hard to measure, because it's very high dimension, and we would need a huge number of samples to do that. So once again, we cheat, just like we did it with the generative adversarial network. Instead of trying to learn a distribution, or to measure the distribution here in the hidden representations, so this would be these two neurons that are representing one point in the latent space, what we do is we train the network to learn not the actual values here, but the mean values and standard deviations of the distribution of this one. So let's say that this neuron here is drawn at random from a sigmoidal distribution, and this one here gives us the mean value of this distribution, and this one the standard deviation. So with the mean and standard deviation, we can draw at random a value here and propagate through the network. So this is the idea. With these parameters, we know what the probability distribution is, because we know the mean, the standard deviation, and that describes these Gaussians. And from these distributions, we can draw at random examples here, and then see what the image is like, measure the error with respect to what the image would be, and backpropagate everything. So now we have another problem, which is how we backpropagate across this gap, because we can backpropagate over products and sums and things like that. But if we are sampling at random from a distribution with those parameters, we cannot backpropagate the error to the parameters of the distribution. There is no way of computing that. But we can do here a transformation of these, or reparameterization of this part. So this is the idea. The encoder is learning values for the mean and standard deviation of the distribution of each of those encoded representations. If we do it like this, if we have a mean and standard deviation and draw at random a value for the hidden representation, we cannot backpropagate the error through here because this is a random sample and not a deterministic operation. But we can change this. Let's suppose that the z value, the one that we have here, is just the mean plus the standard deviation multiplied by some constant. And this constant is drawn at random from an error function which is normally distributed. Now, we cannot backpropagate the error through this random draw from that random distribution because this is just drawing at random and we cannot propagate the error there. But this doesn't matter because we have no parameters to adjust here. This is always the same normal distribution. This one is multiplying the variance here, or the standard deviation, so it will affect the derivatives we compute here, but it will affect them as a constant because now we're computing the derivatives with respect to the parameters. And so we can backpropagate through all the parameters that we need to adjust. We cannot backpropagate here, but we don't care because there are no parameters to adjust here. So this, in sums, is a very neat trick that basically allows us to pick at random the values from this distribution of the encoded representation and still backpropagate the error through the network and adjust the parameters of the network. And now we are forcing the network to make the distributions here, or these parameters, as close to those normals as possible, those independent Gaussians with zero mean and standard deviation of 1. We can also think of this as an extra form of regularization because we are inserting noise into the network, and this forces the network to be more robust to small variations. So remember that one form of regularization was just like this, inserting noise into the network. So this is the trick for variational autoencoders, and one interesting feature that comes out of this is that not only the neurons in the hidden representation, the latent space representation, tend to switch off into just normal distributions if they are not relevant. So the dimension of the relevant dimension of that hidden representation will tend to adjust to what is needed to describe the data. But since we are forcing them to be independently distributed, they tend to focus on independent features. For example, here is an example with the MNIST database in squeezing this data into 2 dimensions. So this would be something like this, where we have 2 neurons here. And this graph represents different values for one of them, different values for the other. And what we can see is that one of them is fixing the content, so the actual number that appears, and the other one, the style. So we can see all the combinations, but they are independent, and we can have, for example, numbers represented with this thick line, or this very thin line, or this intermediate line, or we have the same number represented in different styles, depending on which neuron we are changing. The same thing for faces here. So we have faces of different people that were learned during the training, and different styles of image, and then we have combinations of the different people in the same style, or different styles for the same basic face, and the neurons are learning independent features, or disentangled attributes. So instead of having everything mushed together where we change one neuron and a lot of features change, we can change one neuron and change one type of attributes in the values that are generated then from the autoencoder. So this is a very good way not only to solve that problem of how we're going to generate images from the latest space representation, but also to disentangle the different features that are represented in that hidden representation. So I'm going to jump now to convolution autoencoders. This is not really a different type of autoencoders. It can include everything else, so it's not a different category. But it's just that so far all these explanations are easy to understand if we are considering dense networks, but what we saw with convolution earlier allows us to do this kind of thing. So we have an input image, we do convolution and pooling and so on, and we shrink everything, and probably make it thicker with lots of different kernels. But then if we want to do an autoencoder with convolutions, we also need to do it back to the original resolution of the image. And since we did not see how to do this part, now that we know what autoencoders are, we're going to see also with convolutions how we can do the decoding part. So basically, this applies to all the other types of autoencoders we saw. It's just to explain how we do the decoding when we use convolutions. So basically, when we use convolutions, we need to do the inverse of convolution, of that step of shrinking the data. And unfortunately, you see this term deconvolution, which is rather strange and not really very correct for this kind of operation. Because what really happens when we shrink here, it's not the convolution that is doing the shrinking, it's the pooling. So we are shrinking with pooling, and then we are doing convolutions for identifying features, but we are not necessarily shrinking with convolution. So basically what we want to do when we go back, we can do that with convolution too, the same way that we can shrink with convolutions, but we can also do the inverse of pooling and do this upsampling to restore part of the resolution and then do convolutions over that. So we're going to see three different options. They are theoretically equivalent because all of these are linear transformations, and in theory, when we could adjust the parameters of one transformation to give exactly the same results as the other. In practice, the network may learn things a bit differently, so there are some ways of doing this that can then lead to artifacts. I'm going to talk a bit about that. But we can do upsampling and then convolution. This is the same as fractional stride convolution. I'm going to show an example. Transposed convolution or several convolutions and shuffling. These are basically three ways of doing this increase in resolution. You have this paper here has a lot of detailed explanations of this and showing why they are equivalent. But this is basically the convolution step that we saw in lesson 8 or last week, which you have one input vector that has more, that is longer, has a larger dimension than the output after the convolution. We use convolution with some stride, and what we put in the output vector is the linear combination of the inputs multiplied by the weights of the kernel, and we add this. So this is the convolution that allows us to go from a larger vector to a smaller vector. We can have padding and so on to adjust things. But now, if you want to do it the other way, one way of doing this is transposed convolution. It's called transposed convolution because you can imagine the same matrix but transposed. Now the input is smaller. We are going to use the kernel transposed here in this case, and we are putting in this value of epsilon, the input there multiplied by this weight of the kernel, and here we have the same thing but multiplied by this weight of the kernel. Now we use a stride to put the kernel here, and we again multiply and add. So basically this value of epsilon will be the sum of these two, each multiplied by these parameters of the kernel, and so on. So we're doing the same thing, but we are transposing the way we're doing the convolution, and this results in an output that has more values than the input. So we can increase resolution this way. Fractional stride convolution pads the original data, so the white squares are the original values of the input. Now we add some padding here so that we can stride the kernel in the original coordinates in fractions. So basically this stride here and this stride here are both grabbing the same original values, only they are shifted with respect to the kernel, because we added some space, some padding here. But these end up being the same thing. The only thing that changes are the combinations of the weights that we're using. So if we change the weights accordingly, we can do whatever transformation we are doing with transposed convolution, we can do with fractional stride convolution too. It's just we need to adjust the weights to do that. And the fractional stride convolution, it's easy to see. It's the same thing as doing an upsampling and then a simple convolution, because we just upsampled x, added that padding there, and then did the convolution. So this is one thing that you can do easily in Keras if you want to go from the low resolution representation to higher resolution. You can do upsampling in 1D or 2D. So basically, in this case, it's in 2 dimensions. We have the original x vector, or matrix in this case. We upsample by adding new values here. The padding can be, for example, can be with zeros, can be with the nearest neighbor. So we have an original value here. We fill in the blanks with the nearest value from the original one, and we have these values repeated. And now we apply a convolution to this one, and we mix everything with the parameters of the kernel. So basically this is the same thing as we were doing. We were doing it the other way, applying convolution and then pooling. Now we are upsampling and applying convolution, but it gives us the same result. Another way of doing, but this is not as practical. It's in theory we could do it like this, but at least as far as I know, with Keras or TensorFlow would not be very practical. Would be to start with the original values, the input. We do several convolutions on the input. We use padding so that we keep the same dimensions. But now we shuffle all these different values into a higher resolution representation by putting, say, the first one of this purple and blue here, and then we use red and green, and then purple and blue on the second line, and so on. And this way we are mixing them together into a higher resolution representation. But since these are all linear transformations, it doesn't matter exactly which one you use, because adjusting the parameters correctly, you can get the equivalent results either way. There is, however, one practical problem, because you could, in theory, do that by adjusting the parameters, but the way the network learns may not end up with the right parameters. And empirically, if you use transposed convolution, you have different densities of overlaps across the image or across the one dimension, and so there are pixels that were affected by more weights than other pixels. If the weights of the kernel were properly adjusted, this would not be a problem. We just need to calibrate the weights accordingly. But since the network is learning the weights and is not very concerned with that, what happens is that with these different types of convolutions, you get these sort of artifacts, these meshes, because they correspond to the overlaps of the kernel depending on the stride and the size of the kernel. If you use an upsampling followed by convolution, then typically this is not a problem, because the overlap is more homogeneous. So in practice, it seems, at least according to these results, that it's better to use upsampling followed by regular convolution than to try to use transposed convolution and so on. At least from what the network is learning, the results tend to be better. So to sum up this part, in autoencoders we are training the network to output the same thing as we input, or approximately, minus noise in the case of denoising autoencoders. But the idea here is also to make things hard for the autoencoder so that it will have to find a meaningful representation, something that is useful for whatever purpose we want. So we can do that with changing the dimension, for example, with incomplete autoencoders, or with regularization, so it has some constraints on the weight it can use. And we can even, or force it to reconstruct from corrupted inputs. And if we can solve the problem of how we're going to sample that latent representation, for example, in variational autoencoders, we can then use it to generate the data. And even in the case of variational autoencoders, we can force statistical independence of the features, and this gives us more, or potentially gives us more meaningful features where we can change them independently and still have results that are within what the targets that we want. For convolutional autoencoders, we have this problem of upsampling again, but it's really just the same thing as what we did with the convolution, only instead of pooling, we are increasing the resolution. So for chapter 14 is about autoencoders. You can read more details there. Any questions?